Okay, good morning, everyone. Welcome to our Physical Chemistry 4 lecture. We finished yesterday with our second chapter on the theorems and postulates in quantum mechanics. And we started with the third chapter. Now, even though we already started, I forgot to make a couple of remarks I like to do at the end of the second chapter. So I'd still like to make them here. In particular, I'd like to, so let's start with some more remarks on chapter 2, or let's say some concluding. First of all, in comparison to your macroscopic classical experiment, there are, roughly speaking, two major differences. So the two major differences with respect to classical mechanics. One is that we do have a time-dependent wave function approach rather than the typical ballistic kind of Newtonian or Lagrangian or Hamiltonian approach where you would have a point particle. Right? It's very much at the outset of classical mechanics, we are assuming we have points, right? Mass points, which you can track in space and time. In quantum mechanics, we do not have that. That's postulate number one. So we have a wave function coming from Schrödinger's equation, right? So the wave equation which is the solution of time independent, or in the generalized way, as we discussed at the end yesterday, also for time dependent Schrödinger equation. Schrödinger equations. All right. The reason why you have to do this, there's no wiggling around, is the double slit experiment. If you don't have a wave equation, you cannot possibly account for it. You cannot explain it, right? So you better deal with it. The second thing is then when we measure, we measure discrete eigenvalues. Right? We measure discrete spectrum. This is where the name quantum comes from, right? A quantum is a discrete jump, right? Which cannot be made smaller. If you think about this, right, it's counterintuitive to the classical world we experience on a macroscopic level. Just think about the potential energy of an object and the gravitational field, like this cup. You can vary its potential energy to any value continuously. In quantum mechanics, that's not possible. You either have this energy or that energy. There's nothing in between, right? So this blows our classically trained minds. that the energy should behave like this, right? But it results from the wave ansatz. It results from dealing with eigenwaves, right? And only if you enter the continuous spectrum of dissociative states, you will lose this, right? Or if you enter so many particles that the levels become so close, right, that it looks as if it is continuous, right? But if you consider just your few electrons and your few atoms, you do have the discrete spectrum, and hence you do have these jumps, right? So this is basically your set of eigenvalues. Right? Now, as we also discussed, while you cannot predict for a given system which eigenvalue you're going to measure, you can predict the probability with which you're going to measure a certain eigenvalue. Okay, so in this sense, quantum mechanics is deterministic. It is just deterministic on the probabilities and not on the actual eigenvalues, right? So this discrete spectrum becomes a probabilistic model with deterministic expectation values. Which is just another word for saying QM averages. Okay. So sometimes the non-experts claim that because of quantum mechanics we cannot know the future and so on. That's garbage, right? You can predict the probabilities, right? So you can predict with which probability you have which outcome. So it's very much like predicting a gamble in the casino. You can predict these probabilities, okay? And you can work with them, right? Just like a casino is going to be profitable, we can work with probabilities. There's no problem, right? The underlying microscopic picture has changed from little billiard balls flying around towards little wave packets flying around. Big deal, okay? So from the math and the physics and with a little bit more of imagination, you should, this should not change your worldview, right? You just have to adapt to this interpretation, right? Now, having said all of that, there is, of course, a lot of philosophical interpretation on this, which is quite recent, seen the young age of the science, right? So recent or still in progress. So one example for this is a discussion by Bragg and Manhart, which you can find on the archive. The archive is a preprint server. Many preprints afterwards get published in the peer-reviewed literature, but you should be able to find it here. 1811-02 983, and the title should be something like Fermi's Golden Rule. The second law of thermodynamics. Now, there are certain issues, fundamental issues, which remain. One, for instance, as you can see from this title, is on the reversibility at the microscopic level. So classical mechanics, it's a basic assumption that things are reversible. Now, if you imagine a probabilistic process such as scattering or something, the reverse probabilities are not necessarily a given, right? So there are some fundamental open questions still. Another fundamental open question is the postulate of relativity, that the speed of light is a constant in the vacuum. Yeah, a certain constant which we know in the vacuum, and that nothing can be faster, right? Now, if you think about quantum entanglement on very long length scales, you do have an exchange of information which is supposed to happen instantaneously, right? So if you imagine a quantum entanglement experiment where one part of the experiment begins on the Earth and the other one on the Moon, and you flip your spin here on Earth, instantaneously the spin will flip on the Moon, and thereby information has traveled faster than light. So these are open questions, right? But you see already they assume some quite extreme setup, and it is not clear if this is relevant for chemistry, let's say. Now, there's another point I'd like to make. Which is that we discussed some postulates and axioms, right? And these axioms, they all rest on the hypothesis that the absence of evidence to the counter implies that they are correct, right? So these axioms rest on absence of evidence implies evidence of absence. Now, this is usually considered to be a fallacy. Okay, it's quite a common fallacy. Just because there are no elephants in your backyard, it does not mean that there are no elephants on this planet. But just because you've never seen an elephant, you might presume they don't exist. This can be very weak, right? But it can also be strong, right? So it's weak typically if you haven't looked everywhere. And it can be strong if you looked everywhere. Right, and it basically becomes the exclusion principle by exclusion. So but of course, these things are difficult to falsify. So strictly speaking, these axioms are not part of the scientific method, right? You cannot submit the scientific method to it other than through this assumption. So there are various interpretations of the meaning of quantum mechanics, and I'd like to give one more here. Then Cabello and Sevilla. They provide 12 different interpretations of quantum mechanics, and you should find that at archive.org apps 001 2089. Oh, sorry, wait. I missed one part. Apps and quant Phys. Okay. All right. So I'm sorry, I already started with the next chapter yesterday, but I still wanted to make these remarks. So that also in a sense of explaining things to the layman, you have some material to refer to. All right, so let's return to the variational method now, to chapter 3. And before we enter here, right, what do we have? We have Schrödinger's equation, giving you the energy as the expectation value of the Hamiltonian. Okay. Now, we do know the Hamiltonian. Okay. Typically, that's what defines our system. We would like to know the energy or some observable, but we do not know the wave function which we need to calculate this integral. Generally not known, right? But what we also know is that we have eigenfunctions well, not generally, but often. So we know that your H, when applied to some small psi, will give you some eigenvalue on that eigenfunction. Okay. So this means, at least in principle, we might have a set of n eigenfunctions, and we discussed this in the theorem number 3, that we can use these eigenfunctions to series expand any state function. Okay, most notably our big psi, right? Okay, so this is why theorem 3 is so cool. So if you manage to get some eigenfunctions for your Hamiltonian, then you can use the set of eigenfunctions as a basis in which you series expand your big psi. Okay, so that is nice. This basically means we can write our big psi as a sum over our eigenvalues, eigenfunctions and eigenvalues like this, right? So we still don't know psi, neither the small nor the big, right? But we know a way to formally write it down, right? And if you suppose that we know the Schrodinger equations for our eigenfunctions, right? So this, just to clarify things, this is a bunch of n Schrodinger equations. And this is also a Schrodinger equation. Right? There's not just one Schrodinger equation, there's many. Somebody's talking about the Schrodinger equation, you should always ask yourself which one. Somebody's talking about the energy, you should always ask yourself which energy. Right? Enthalpy, is it a potential energy, a kinetic energy? There's tons of different energies, right? The variational method now is a procedure which allows us to determine these coefficients. Okay, so that's why this chapter is a very nice topic, right? So you can, we've laid the basis in chapter 2 for all of that to happen now. Okay, for instance, through theorem 3, right? By knowing about these eigenfunctions, by knowing that they must be orthogonal according to theorem 2. So we know all of this, right? So let's get to the beef here. So our first subsection is going to be the theorem. Okay, and the theorem states that this thing before we do this, hang on. I have to be a little bit more specific here. Up here, this is strictly speaking not true. The way to write it is your big psi gets approximated by some trial wave function, which we define to be the series expansion, right? This is a trial wave function. Okay. Now this this expectation value, we can approximate this by, no, let me write it different. We write the expectation value with our trial function, which is nothing else than your usual integral And the theorem is that this is larger equals the lowest energy you can have. Okay. So it's a minimization principle. It means that this is always above your energy. So we can prove this. Okay. So and we're going to use the series expansion from above. So okay, so I just substituted my phi by the series expansion. And now I can pull my coefficients in front. And I'm left over with my expectation value of eigenfunction k, Hamiltonian eigenfunction j. Now, this gives me my eigenvalue k, sorry, my eigenvalue I, my eigenvalue j for my eigenfunction j. And so I have k, j, ak, aj, ej, e tau, psi k, psi j. And this, I believe, was our second theorem, is the Kronecker delta for orthogonal eigenfunctions. Okay. So this means this entire expression only survives if j equals k. Okay. So this means one summation dies. It means we have ak squared and ek. Now, we do know that ek must be larger equals E1. Right? So as your k goes up, right, your eigenvalues go up. And so this is the lowest eigenvalue. And so this means that we have here something like E1. And E1, of course, is independent of your summation of k. So I can pull it in front. And now your AK is the probability for state k, right? And we know that the the set of eigenfunctions is supposed to be complete. So the sum over all probabilities should just be 1. And hence, you could show that what's written here on the left must be larger equals the lowest energy in your eigenvalue spectrum. Okay. So one question is still if our phi is not normalized. We can easily achieve this by using a normalization constant. So you say 1 must be equals our normalization constant, and we want this in every phi, right? So right. And from this follows that n squared is 1 over phi. Right. So we can say now our energy value for a given trial function, we can define this to be this thing. So let me, this just to be formally correct, you write your normalization constant also possibly as a complex conjugate, but in reality this never, it's always real. D tau phi Hamiltonian phi, and that is then nothing else than phi h phi phi, right? And this thing, because the n squared is just a constant, must still be larger equals E1. Okay. So this normalization procedure you should have seen already, but this is basically how we arrive at the expression which forms the basis for the variation method. So basically what this is saying is that, so the meaning, right, is that your Hamiltonian is fixed, that's your system, right? But you can play with the phi, right? Play with phi as much as you please, resulting normalized expectation value W will always be above E1. And so in other words, you would like to get, you can try if you can verify such that your W approaches E1 as much as possible, which means you can minimize W in the space of your trial functions. Right. Minimize variational integral W in space of phi. Once it's minimal, right, you're as close to E1 as you can possibly get with the given choice of trial functions phi. Okay. So it turns out that this is a fast converging problem for this some trial function, and its deviation from E1, right? So you will quickly minimize this. But if you have access to the true wave function, you can also measure the difference between your trial function and the true wave function, right? And there, this difference is not as fastly converging, typically. Not as fast for phi minus psi. Okay. In other words, good energies do not yet imply good wave functions. Okay. Now you need the wave function, for instance, to calculate something like a dipole. So with a crappy wave function, you might be getting a really nice energy, a very good energy. But if you use that same wave function to calculate the dipole moment, it could be that it's also really bad. Right? So this is a remark, and I actually want to make two remarks. This is remark A, and remark B is that the way we see this E1 is like a ground state energy. So in all the possible solutions, right, that's the lowest you can get. So this begets the question, can we use the variational theorem for every state? Can we use it for the next one as well? And the answer to this is yes, in principle. Once you did it for the ground state, you can exclude that solution. And then you basically reapply the variational theorem for the first excited state. This is possible. But we will not go into much detail in this course as to how we would do this. Yes. So we will not discuss the details here. in this course. Right. For this, you need to take a more advanced course in quantum mechanics. All right, are there any questions so far? That's not the case. I would now like to discuss two examples where we make use of the variational theorem in a very immediate fashion, right? Without a fancy expansion. The example number one is going to be the harmonic oscillator. The quantum harmonic oscillator in one dimension, okay? This means this is the same as saying my Hamiltonian is minus h bar squared over 2m dx, second order, plus, that's the kinetic part, 2 pi squared nu squared mx squared, okay? Now the prefactors can be arranged into single force constant. The important thing is the x dependency, right? So this is our Hamiltonian, and it is a function of x. Again, as in previous examples, we will not solve this ourselves, but rather presume that you looked at this already. So you should have discussed already the Schrodinger equation for the harmonic oscillator and how to arrive at something like the following, where you say, as an ansatz, we will say our trial wave function is going to be e to the minus cx squared. Okay. Now, this is not a bad ansatz, right? It's squareable. You can integrate it, right? It's just a Gaussian. It has no dimensions, and the c is the c constant is some characteristic length scale. Let me note this down. Squareable, integrable. C is characteristic length scale. And what's also nice is actually we don't even have a node. So no node in ground state. So for all these reasons, this is a reasonable ansatz. Of course, this is not a sufficient exhaustive list of criteria, but this is sort of the dirty laundry list of things you would like to have in an ansatz, right? Okay, so let's go and calculate then, okay? So we go to watch the time. We are already approaching the full hour. Now there's no complex conjugate, right? We have chosen a function without imaginary numbers. I immediately split the two integrals in the kinetic energy and the potential energy. And I pull all constants in front of the integral. And I know that my potential is multiplicative, so I can immediately pull together the left-hand and the right-hand side wave function. Okay. We reached 10 o'clock, so we have to stop now. I think, I hope this example is sort of illuminating what this means in practice. Just let me briefly tell you, if you look at this expression, everything is known except for one thing, right? And that's this length scale C, right? This will tell you how your wave function of your lowest, the harmonic oscillator in the ground state, how wide this wave function is, right? Is it wide like this or wide like this? This depends on the C. And given this ansatz of the wave function, right, we now want to find the best possible C, which will minimize our energy, right? So we will look for the derivative of the energy with respect to C and set it equals 0 and then solve for C. It's as easy as that, right? It's basically math from high school. You should all be familiar with. But we won't do that now because the time is over. I'd like to thank you for your attention. We'll do this next week, and I wish you a good remainder of the week. And I would like to say bye-bye now. Thank you.
Bye.